next one in line, it's actually 3. So we have Alexa Kachler, Carlos Fenoy, and Bettina Crippa, all of them coming from Roche. And they are going to talk about Juno from centralized to personalized HPC. Thank you so much.
Yeah, welcome. Thank you. So with my colleagues, we will present our centralized personalized HPC solution. Juno.
Alex, please, the mic closer to the mouth.
Sorry. I will start with a general concept and architecture. Bettina will follow with application layers, and Carlos with observability. No. Yeah. We have all seen users complaining about resources. I have not enough CPU, GPU, I cannot wait for my job to start, and etc. When all these complaints are usually not really founded, sometimes it just highlights some limitation on our shared models. Resource is always a huge thing, especially on GPUs demand, which are growing beyond the limits and capacities. Demand for ephemeral and special hardware, and also special things like SLAs. To tackle these issues, we defined some special requirements: automated deployment, ephemeral environment, access to modern hardware, and CPU or GPU or specialized accelerators, lightweight clusters, security by design to follow all our security constraints we can have in-house, and of course portability is a key thing to be able to move a solution across different providers or regions. Traditionally, HPC is usually shared environment. This comes with some drawbacks like complex security setup, management, and etc. So personalized cluster will help us here to cut all the problems in smaller pieces. Our foundation for cloud is AWS, therefore we move to Parallel Cluster. So Parallel Cluster is an SDK based on Python-based, open source. It provides a set of tools to manage, deploy clusters on AWS. Everything is infrastructure as code defined in a single YAML file. So it's really straightforward to define a cluster with all the dependencies. You have multiple tools to manage a parallel cluster. You have CLI access, API, even a web interface, and Terraform extensions. The documentation is quite detailed on AWS website, or in GitHub you will find all the details how to use Parallel Cluster. Before deploying any cluster, you need a set of components for Parallel Cluster. So one of the first one is having a specialized image, an account where you want to deploy the cluster, and obviously a region, a target region, a set of security items like policy, security groups, customization scripts, and storage, and networking. The first key component is the image. Parallel cluster needs a very specialized image, and AWS has a very detailed documentation how to build this image. It's not a straightforward process, because building this image is quite complex, and especially if you have to deal with security restriction in your AWS environment. So AWS is providing pre-built images, but this kind of image cannot be used in our environment. Therefore, we decided to build our own image, and our cloud team is providing us a base parallel cluster image, and we are using Git CI/CD pipeline with Packer to customize this image. We need customization because we need to add additional packages in this image and software. This is also a key point because we do not want to overload any boot scripts from Parallel Cluster to not extend the boot time for the EC2 instances. We started Parallel Cluster with Alma at the beginning, but it was not very compliant with what we have in-house and some of our software. So we moved after from Alma to Rocky Linux because it has a way better RPM compatibility with our Red Hat Enterprise solutions. The other key thing is to not forget is AWS Parallel Cluster needs a specific version for each image. So each time you are building a new image, you need to tie it with the current version of Parallel Cluster. And you cannot mix them in a single cluster. So deploying such an environment in a very strict cloud solution like ours is not easy. You cannot use the default provided by a Parallel Cluster. Even if Parallel Cluster is providing a lot of automated things, it will deploy all the dependencies for you in the background. That's not possible. It was not possible in our case. So we had to define our own policies, our own scripts, and to tackle all these small problems. So one of the most complex things we had to deal with is the DNS management. Parallel Cluster comes with a predefined and configured DNS setup for inside the cluster, but we needed also to register all our compute nodes and head nodes in our enterprise domain. The complexity here is that the DNS management is not done in the same account we are using to host our clusters. So all Route 53 setups are done in our production environment, and therefore to get access to this account from the other account, we had to define a set of rules and trust policies. So we are using GitLab to create the new zones, and the EC2 instances are using a specialized script to register them in this created zone. So, and GitLab is using OIDC for the authentication, so that is fully transparent once you have defined the proper trust policy and policies in your AWS account. Obviously, AWS is offering a lot of storage solutions, so EBS, FS6 for Lustre, FS6 for OpenZFS, S3, and so on. We decided to go with FS6 for Lustre because, with intelligent tiering because it offers the best performance versus cost ratio. All the FS6 storage volume are created at the cluster creation, but they are not destroyed when we are terminating a cluster because we want to be able to reuse the storage if needed or to keep it longer than the life of the cluster. All the data we are hosting on the cluster are considered as scratch data, and we are enforcing a no backup policy. So people are forced to copy data from the original point of truth to the cluster when they need something. Therefore, there is no need to secure any data on the cluster. We have also the ability to mount storage from the on-premise storage in the cloud on the cluster, but this is not done by default. That is already on demand in case by case. The deployment process is fully automated. So for most of our deployment and automation, we are using GitLab. So the dependencies are managed by OpenTofu. So OpenTofu is managing the creation of the zone in Route 53 in our prod account, and also the creation of the FS6 storage. All the status are stored in S3. The config file for the status file for OpenTofu are stored in S3. Sorry. All the parallel cluster management is done directly by CLI, not using any OpenTofu or Terraform solution, because the Terraform extension for parallel cluster are outdated, and they are not providing all the details for the current version of parallel cluster. So we had to use directly the CLI for that. That is the general architecture of Juno. So on the top left, you have the admin using the parallel cluster tools to interact with the parallel cluster deployment in AWS. So all the deployment are going through CloudFormation because they are using templates for that. In the central piece, you have the head nodes with some EBS local storage to store some configuration and local software. And on the right side, you have all the queues with the compute nodes. User can interact with the cluster through various pipes. So we have the web interface based on Open OnDemand and SSH. We also, as mentioned before, we can mount on-premise storage directly to the head nodes or the compute nodes through NFS on demand. Something I have not mentioned is we have the accounting database in RDS. That's on the top. Yeah, jumping on Slurm. So one of the goals of this Juno setup was also to have something very lightweight and very easy to manage on the scheduler side. So we are trying to put as less as possible special configuration on Slurm on these dedicated clusters. So we have one partition for each kind of CPU or GPU resources, only one course, only one group of users, and sometimes we have a dedicated partition when we get access to reserved resources. We are also providing REST API access, and the API, some API is connected to our SSO to have a very secure and transparent access for the user. And we have an application stack which can be divided in 3 main pillars. We have local application that covers everything what you can install directly on the head nodes, on the local nodes. We have the centralized application stack. We are holding our scientific application and obviously our remote and interactive application setup based on Open OnDemand. And now I will hand over to Bettina.
So thank you. So my colleague Alex, he was presenting to you the basis and the deployment of our Juno clusters. And I will focus on one level higher, so the applications. I will present to you the application stack that we are using and also the portal solution that we use for providing interactive application access to our Juno clusters. So let me start with, Let me start with our application stack. So that's called ROCks. It's our Roche computing stack. And we provide this application stack on our on-prem clusters, on all other Linux clients that need it, and also on cloud systems like Juno. And this is a solution that is inspired by Compute Canada, EASY, and also the work of CERN. So on the bottom, you have the host operating system, so that can be any Linux distribution. It comes with GPU drivers, and the network config, etc. On top of that, we put a compatibility layer with Gen 2 prefix, so we add all the common Linux libraries that one needs. So we have a leveled ground across all the Linux distributions. And on top of that, we then put our application, so that's the software layer. For that, we use EasyBuild to build all of our applications, and we provide 3 builds for 3 different CPU architectures. And to distribute all these applications, we use the file system layer. So we use on our on-prem cluster GPFS, so an IBM solution, and on all the other remote clients, we use CERN VMFS, or short CVMFS, which is an HTTP solution that is globally available. It is, does not need any tight coupling and has a local cache available, which makes it fast. So we provide ROCs on Juno, but I will now show you why this is not enough, and we had the need to additionally have a portal solution for interactive apps. So Juno has a big power, so it provides access to a lot of compute resources in AWS. But the problem that we have with some of our scientists when we speak about cloud infrastructure and CLIs, it can be a bit intimidating for them, and it's difficult for them to use. Additionally, some of them might just have a need for interactive application or remote desktop environments to, for example, do some image analysis. So if we just provide the application stack, there would kind of be a risk that the resources would be underutilized, or some scientists just might say, okay, we do not use these Juno clusters. So our solution for that was to deploy an Open OnDemand portal for them to bridge this kind of gap between the cloud cluster and the usability for the users. And why Open OnDemand? So in fact, we have very good experience with Open OnDemand. We use it for our portal solution on our on-prem HPC, and our users really like it. And you know, if they have a solution that they really like, they say, oh, hey, I just want the same. Can you put Scoop, that is the name of our on-prem portal, can you put that on Juno? So the expectation is they have the same graphical experience, everything looks the same, they do not need to learn something new. So before I present Scoop on Juno to you, let me tell you what Scoop is, or on our on-prem portal. So Scoop stands for Scientific Computing Community Portal, and as I already mentioned, it's an Open OnDemand solution. And the really nice thing for us, it's a community collaboration between all the main Roche organizations, and we are working together in providing one portal for all of our users. So this was not always the case. So before we had, so each organization had their own portal solution out of different reasons, because we wanted to provide our own design, our own news, our own organization-specific application, and links to our own doku. And then Open OnDemand came out with this nice feature of profiles for us, which gave us exactly a solution for that. So each of our organization now has their own profile where they can define their own landing page, their own links to documentation, and additional to the shared applications, also some organization-specific applications. So this delivers kind of a very nice graphical access for our users to interactive applications, and they really like it. And all the code is in GitLab, so we follow the GitHub's approach. So everybody who wants to can contribute, can open some merge requests that are then evaluated by the Scoop community and then merged. So when we're speaking about bringing the Scoop portal to Juno, we followed the strategy that we wanted to reuse the same Ansible code base that we already used for deploying our on-prem cluster. So reusing the same roles that we had also on-prem. And yeah, the goal was that really the users do not see any difference between the on-prem cluster or the portal deployed on Juno. So they see the same UI, the same tools, and the same branding. And for the engineering, since our Juno clusters are kind of independent from the on-prem cluster, and also between them, they are independent of each other because they are for different projects, for different groups. They don't share any file system in general. We decided that each Juno cluster gets their own dedicated portal that is deployed on the Juno head node. And okay, that sounds straightforward, but we also had some challenges when deploying the same portal then on AWS. Because on-prem, we had have a static hardware. So for all the interactive jobs, we basically have one type of GPUs that the users can use. And on AWS, everything is more dynamic. Different nodes can be spinned up, different GPU types, different partitions in the different Juno clusters. And so we needed some more cloud-native adaptation, and I will mention it a bit later on. So concerning the architecture of the solution, so the users directly access Scoop on Juno over their web portal, and the Scoop portal is then deployed directly on the Juno head node via Ansible. And during the deployment, we directly set up SSO using OIDC that is integrated with our enterprise ping federate, so the users can easily log into it. And Scoop is then directly integrated with Slurm, which can then dynamically run some interactive jobs on the compute nodes. Okay, and concerning the deployment, so we managed to have it fully automated with Ansible. So all of our code for the deployment of the portal, but also the applications, they all live in GitLab. And then on each Juno head node, we run the Ansible playbook with the respective inventory file for the respective Juno cluster that then installs all the dependencies, installs the portal, clones the applications from GitLab, and sets up the ping federate or ACD configuration, and also automatically directly creates SSL certificate for the portal. So here we have really no manual intervention. And one thing I wanted to highlight, because of this transition to more cloud-native solution, so one of the problems that we had was, each Juno cluster has kind of a different setup. Compared to our on-prem cluster that has a static setup, it's more dynamical. And so if I provide application form to users, I wanted them, this is mainly for GPUs, for them to be able to choose the respective partition and GPU types that are available in this partition. And I didn't want to do this manually, because maybe next week we add another node with another GPU type, and not every time we do that, I want to just mess around with the forms and add something. So for that, we decided to use dynamic forms. So each time the form is called, a backend script will be called that basically just queries Slurm in real time, gets all the partition info and also the information about the GPUs. So for each of the Juno clusters, I do not really have to touch anything, but okay, each time the form is called, this little script is running in the background. And when the users then click on the submit button, again, I kind of translate this nice GPU types for them to some AW instances where then Slurm will start the job. And how does the portal then look like? So it has basically the same branding and UI than also our on-prem cluster. But additionally, we include here a cluster monitoring dashboard so that users can directly see how utilized the cluster is and what their jobs are consuming. Then here on this portal, we do not have any profiles to choose for them because we only provided this profile to our organization. In the head, they can find our documentation, how to create a ticket with us for support, and how to join our community chat. And as applications, we currently provide Jupyter, VS Code, RStudio Pro server, and remote desktop application. But this is currently under development, and if the users need more application, we will just add them there. So I just want to highlight a bit how we add this nice dashboard. So we wanted that for the users, it's kind of zero context switching. So if they are on the portal, they do not need to go to any other dashboard in Grafana or so to see how the cluster is utilized. So they directly see it on the main page of the portal, and they can see the resources that are used. And Open OnDemand is kind of nice for that. It's very simple to integrate this functionality, so simply with the HTML widget. And during the Ansible run, I just include the respective dashboard for the cluster that we have in the deployment, and then it's there. And with that, the users, I find it quite nice, have this real-time insight of how the cluster is utilized. And my colleague Carlos will now tell you a bit more how we get this data for the monitoring from the Juno clusters. He will speak about some use cases and some pros and cons of the solution.
Thank you very much, Bettina. Yep. All right, so I'll talk a little bit about our observability setup and monitoring. Yeah. So obviously, when you have dynamic environments, knowing how much they are used and how they are used, it's important, right? So we try to put some effort on designing our monitoring setup. Also, you know, monitoring is one of my loved hobbies. So we wanted to have something tightly integrated with Parallel Cluster. I don't know where to look. But yeah, so we wanted something automated that would allow us to deploy the whole solution on cluster creation. We wanted to have also centralized management, right? So if we want to make a configuration change, as we have many different clusters, we don't want to go to each of the clusters to change something manually. We are using Grafana Cloud, so our main agent to collect the metrics that we chose was Grafana Alloy, that would allow us to connect all the metrics and send them to our Grafana Cloud environment. And as we also have different environments, we also need to identify to what cluster or what use case each of the metrics belongs to. So we're using this cloud-aware tagging of all the metrics to collect the information about the cluster name and the instance type. So we can get more precise metrics and logging. So I mentioned we're using Grafana Alloy, and Alloy is great. It provides something around like 430 metrics by default. So you get a lot of information by default, right? You get CPU memory, CPU usage, memory usage, network, OS metrics. But we're on an HPC environment, right? So if you're monitoring web servers, that's great. That's all you need. But on an HPC environment where you may have multiple jobs running on the same node, that's not enough. So instead of replacing Alloy, we were happy enough with Alloy for monitoring the infrastructure part, but we wanted to augment it. And we look around, and in the past, long time ago, in my previous life, we already did something, some integration with Slurm. There's this Slurm InfluxDB plugin that allows for real-time monitoring of jobs, but we're on the 21st century now, so we needed something more flexible and better suited for our needs. So looking around, we found JobStats. For those of you who are not familiar with it, JobStats is a project from Princeton University, and it's mainly meant as a monitoring platform for CPU and GPU clusters with Slurm. So this project suited perfectly for our use case. JobStats is not just one single tool, right? It is a platform. It provides plenty of tools. I will only focus today on the JobStats tool itself. But if you're interested after the talk, I suggest you to look at all the tools that they offer. They are very useful for cluster administrators or support teams to get more insights on how your infrastructure is used and support your users. So how do we use JobStats and how do we integrate it with our Alloy and Grafana Cloud setup? Right? So I mentioned we have Grafana Cloud. Why we're using Grafana Cloud? Because it's a managed solution that we already have in the company. So it's one less tool that we have to care about, right? So, and when you're managing an HPC, you keep adding tools and tools and tools, and at the end of the day, you have too many things to worry about. So if someone else is taking care of our Grafana and monitoring stack setup, that was a great solution for us. So for us, we just pointed JobStats to Grafana Cloud, and that's it. How JobStats works, so it needs several exporters. For those of you who are familiar with Prometheus, they are the usual exporters. For those of you who are not familiar, the exporters are just metrics collectors that expose an HTTP endpoint that usually Prometheus scrapes. In our case, because we're using Alloy, Alloy is the one that scrapes the metrics locally and pushes them to the Grafana Cloud. Usually on traditional deployments, you would use the node exporter, that is the one providing all the system metrics. Alloy already provides that functionality for us. And JobStats requires a couple more exporters. One is the cgroup exporter that makes this integration between the usage of the system with the job, the Slurm job that is using it. Right? So all the documentation is on the JobStats website, and it's great. And they have a specifically modified cgroup exporter to support Slurm cgroup B1 setups. If you're using cgroups B2, you can use the standard cgroup exporter. And the additional exporter is the NVIDIA GPU Prometheus exporter that then exposes some additional GPU metrics for your jobs. Obviously, just having the jobs information when you have multiple clusters is not enough. So I already mentioned we are adding or augmenting the metrics with additional information based on what cluster the users are running, or what instance type, for instance, right? So we can get some more additional information on this. One of the drawbacks of our setup is that we have a maximum or minimum time resolution of 1 minute. Right? We cannot gather metrics faster, but that's because of our Grafana Cloud setup and how we get that service. If you have your own Grafana setup with your own Prometheus, that's not a limitation that you have to follow, and you can connect as often as you want. For us and our use cases, 1 minute is good enough. We don't need high resolution metrics to see exactly how the jobs are 99.8, 99.7, 99.8% usage. Just knowing that they are around 99%, it's fine, or 50. Good, so how does JobStats work, or what does it offer to the users and the admins, right? So one of the nicest tools that JobStats provides is the JobStats CLI. This provides a very easy interface for the users to see exactly how their jobs are doing, right? So it provides, you have at the bottom, you have this usage command. So you just run the JobStats command with your job ID, and you get what you can see on the right side of the slide. That is just the summary of your job. What is the state of the job, how many cores you requested, how much memory you requested, runtime, time limit, and so on. Then you get the overall utilization, and that is our most loved feature of this.
So you can see exactly what is the efficiency of your job, right? You requested 200 CPUs and not only using 50, then your utilization is going to be very poor. And also for the memory. If your job also uses GPUs, you will also get a GPU utilization summary here. Additionally, at the bottom, jobs that is highly configurable, so you can add some nodes also based on this information. So if your users are underutilizing their resources, you can put a warning, your job is over-allocating resources, please lower or reduce your resource allocation. Or in our case, for instance, we add our Grafana link so that the users can go to a dashboard and see exactly over time how their job was using the resources. And this is more or less how the dashboard looks like. So it's a typical Grafana dashboard that allows the users to select a job ID or a cluster, a job ID, and if they want a specific node. And then they can see over time how their job did, right? And you can see the CPU utilization of the job, the memory utilization, but also in case you're experiencing some performance degradation on your job, you also have the node statistics for these nodes where your job is running, right? Just in case you have some neighbors, noisy neighbors disturbing your jobs. Yeah. So how does this all fit together, right? What do we use this for? Because, yeah, observability is great, having dynamic clusters is great, but what do we use them for? So we have so far several use cases in Roche that use Juno. One of them would be chemistry simulations, where they have very spiky workloads, and we cannot accommodate these use cases on-prem on a timely manner to get the results. Right, so in this case, we can provision additional resources on the cloud. The users run their simulations there for around a month, and then we destroy the cluster, and the users are happy, and we are happy. Other kind of use cases, AI workshops, right? As Alex mentioned earlier, GPU demand is pretty high, so we cannot always accommodate demand to run a workshop where every participant needs a GPU. So in this case, we had a one-week workshop where the participants needed a dedicated GPU to run some models. So we provisioned a 32 GPU latest generation that was available in AWS at the time for the participants to work with it. Image analysis as well. This is an ongoing project that, as you can see, it says it's unlimited time. That is ongoing at the moment they are developing their framework for the image analysis. So they also have some dedicated CPUs and GPUs, so they can run their applications. And as Alex mentioned as well, one of the advantages of running on the cloud is that you can also test the new technologies. So we're also testing ARM and using the cloud to add additional applications to our ROC stack that support ARM for future architectures, right? Or future deployments on-prem. So this allows us to work with new architectures or not so traditional hardware that we don't have available on-prem without committing to buy the hardware for a long time. So to tie all together, what are the benefits of what we've presented today? What are the benefits of Juno versus just going with parallel cluster and have a massive cluster for everybody to use? So having dedicated environments simplifies massively our authentication and authorization. Right? We only have one use case running on a cluster, so you don't have to worry about file permissions, login permissions, or any of this, because only one group that they already work together has access to the environment, and they are entitled to share their data. We also provide a similar environment to the on-prem clusters. So the users are familiar, and it's easier for them to adopt the new environment on the cloud. Having dedicated environments also provides easier accounting, right? I can say, okay, you run a 400 CPU job, all goes to your project. You leave half a node idle, that also goes to your project, right? Nobody has to take care of the idle resources because the users are all accounted for whatever they request. We also reduce the neighbors' noise, right? When you have a shared cluster, you don't know who's running next to you, who is massively impacting the file system or the network. Usually, all of the users are going to be running similar workloads on these kind of environments. And it also helps us reduce the blast radius whenever there is a problem or we have to do a maintenance. Right? If we have to recreate the cluster, we're only affecting one use case. We're not affecting the 100 different use cases that we may have. And the environments are self-contained, right? So if we need to move from one region to another, okay, we move the imaging project from Stockholm to Spain. We are also only affecting one project, and we are able to move just that one project because we need more resources, and that's what we can get in the existing region or newer resources that are not available there. And we're also able to offer guaranteed resources, right? When you're running on-prem, it's very difficult on a shared environment to be able to justify, okay, I'm going to dedicate these 20 nodes to this specific group, because then you will have the typical user saying, oh, but you gave the nodes to them, I also want my own nodes, and then at the end, everybody wants their own cluster, right? So this is the solution to give them their own cluster. Obviously, not everything are rainbows and unicorns, right? So there are some drawbacks to the solution. One of them, of having a dedicated environment, you have long startup times, right? Starting an instance on AWS, it's not immediate. It doesn't take hours, obviously, but it takes some time, and depending on the instance type, it takes longer, right? Large GPU instance types take 15 minutes or more to boot up and be available in Slurm. We do have some duplicated components, right? We have duplicated head nodes per cluster. We may have duplicated file systems and some other redundant infrastructure that if you all were sharing the same infrastructure, you would not have. We also have these resource silos, right? Where you may end up with idle resources because a user just requests one CPU and you have to put a whole instance just for that user. And then maybe you end up with 31 cores being unused that on a traditional environment somebody else would be able to use. And obviously, it also adds some management overhead. Having multiple clusters is not the same as having one cluster, right? We try to simplify the clusters as much as possible to reduce this overhead and make the configuration simpler and easier for us to manage, but still, it's multiple clusters. And what do we want to work on from now on our Juno solution, and what you need to take care or take into account if you want to deploy something similar? So some of the improvements we want to work on, we want to continue improving the automation and self-service of the solution. So Bettina and Alex already presented that almost everything that we have is automated, but we also want the users to be able to request a cluster and us not having to create the template manually and upload it to Git and so on, right? So having a more automated self-service for the user say, okay, I want a cluster. Some of the admins say, okay, yeah, you can have a cluster, and the cluster just goes and gets created, right? We don't have to go to do all the configuration manually. We also want to explore additional file system options, right? So we chose FSX for Lustre because with intelligent tiering because it's performance, price, a good compromise. But Amazon recently just opened the S3 files access, for instance. And we see a lot of adoption of S3 in Roche. And then the users want to use the S3 data that they have on the cluster, and that is a little bit not so easy to do if you want to use it as a POSIX file system, obviously. And also, we want to work on a way of minimizing the inter-availability zone transfer costs. So whenever you get resources on AWS, you may not be able to get them on the same availability zone. That's like one data center in AWS, right? One region can have 2 to 3 availability zones. And if you get them, I don't know, let's say we're in Spain, so you have a data center in Zaragoza and a data center in Teruel, right? If you get half your cluster in Zaragoza and the other one in Teruel, you're going to be paying a fortune just to transfer data between the 2 data centers, right? And AWS is never going to guarantee that they give you resources in one specific availability zone. Also, when you get a resource reservation, you may have your cluster deployed in Zaragoza. You get a resource reservation because you have an AI workshop and you need GPUs. And AWS may say, oh, we're going to give you the reservation in Teruel, right? So then what do? You have to move your cluster or incur all these massive transfer costs. So that's something that we want to work on to optimize as much as we can. Some considerations if you would like to do something similar. AWS is slowly retiring the parallel cluster support because they came up with their own managed service that is called this parallel computing service. Right? It's still not available everywhere, and there are still some functionality that is not there. Right? They do not support the Slurm B2, cgroup B2 functionality, for instance. Or the REST API is a little bit difficult to use. So, but it's something that we want to also evaluate in the future and see how that will affect our deployments in the future. The instance availability, it's also a concern, right? As I mentioned, you may end up with instances on different availability zones. So, and some of the existing regions are not getting newer hardware, right? So if you want to get newer hardware, you may have to end up going to a different region just to be able to use it. So it's also that we also need to take into consideration when we create a new cluster. It's okay, how long is this cluster gonna last? What kind of instances do we need to make the decision on where to place it? And parallel cluster and parallel computing service, it's not available on all the regions, right? It is now available in Spain. By the time we did the slides, it was not, right? And there are still some regions that don't have parallel cluster or PCS available. So that's also something that you need to take into consideration when you deploy. All right, finally, the conclusions of our presentation. So scaling out to the cloud enable our scientists to reduce the time to results, right? They get access to more resources, so they can get their results quicker. Providing a unified experience, right, reduces the onboarding friction, right? When you provide a similar environment to what you have on-prem, using the same queuing system like Slurm, using the same application stack, the same portal, the users tend to adopt your system faster and easier. And dedicated environments also provide predictable timelines, right? So if you need to run your workloads on a timely manner, having your dedicated environment can guarantee that. While if you're running on a shared environment, it's, okay, today I have to wait 2 hours, tomorrow I have to wait 2 days to get to my results, right? Cloud environments provide faster access to state-of-the-art technologies, right? I don't know if you tried to order some GPU servers lately, but the delivery times are terrible, right? Well, if you go to the cloud, yeah, you have to pay a little bit more, but you can have them today. It also increases the flexibility and delivery speed, right? Again, the same. Delivery times of hardware are pretty long at the moment. Going to the cloud, you can set up your own HPC environment today and destroy it tomorrow, right? And it also allows a solution like ours for easier experimentation without long-term commitments. That's also very important when you're just experimenting with new hardware or new technologies, or just have a short-term project that you don't want to pay for a hardware that is going to depreciate in 3 or 5 years. So that was all from us. Thank you very much. And we'll take questions now.
Okay, we have time for questions. If nobody is asking things, I'm going to ask a lot of things. So, okay.
So thank you very much. Impressive what you built, so congratulations. So my question was regarding all the observability part that you, so I'm curious to know if you are putting all these nice things to the user and if they are really using or they are interested in checking, and how, if you have techniques to make it, because usually from our point of view, we like to put all these dashboards and so on, and at the end, except when there are issues or really they don't care, usually they don't care on efficiency, so if the result is fine, so you have done a very nice thing and the utilization is. So I'm wondering is how are you dealing with this?
Yeah, so users usually only contact support when they have a problem, right? But at least having this kind of tools provides them the self-service to be able to identify by themselves if there is an issue before they contact us, right? And they tend to use it when they have a problem only, right? But something like JobStats also serves us to be able to contact the users, right? Because it monitors the efficiency of all the jobs. As I mentioned, there are several additional tools in JobStats, right? It's not just the CLI or the Grafana dashboard. It also provides some automated notification system for users if they are under the threshold of the utilization that you want, or it can even kill jobs by itself if someone requests a GPU and they are not using it, for instance, right?
Yeah, I have a question. So have you assessed on average what is the cost of maintaining those AWS instances, I don't know, per year, per month, something like that, in comparison to the local infrastructure?
So you mean just the management or the overall cost of such a cluster deployment?
The cost of the AWS instances that you are paying for.
Yeah. So that it's under control because we have system monitoring our usage. We are using special tags on all the resources we are deploying, so we can directly look which cluster is using what, and that's linked to our project or our client. So yes, we have a very good overview of what we are using for each cluster, and the footprint is quite low. So in regard of what we are using on other deployment on AWS, the footprint is very low. But the surprise when we looked at the first deployment we had is the storage. We are probably burning most of the money in the storage, in the FSX storage, and not in the compute part. So that was the surprising outcome of that.
Yeah, my question is also more quantitative, I would say. So how much does it cost to maintain such a cloud infrastructure for Roche, for your company? Have you assessed? I mean, or do you have a mean to assess it? I mean, I'm curious because I would like to compare this, as this is a very flexible solution, and of course is ideal for experiments, for point-in-time needs and that stuff, and that's the great thing of the cloud. It also has to be taken into account how much it costs to have, I mean, as an average or an estimation per year or something like that, in order to see whether it's worth to have this cloud infrastructure, I mean, this cloud service level agreement with AWS, or have a local infrastructure.
Yeah, I don't think we have all the numbers now because this is quite new. So we just started to deploy that. And we have our overall cloud budget. So that's under this budget umbrella. So as long as everything is fitting there, we are fine on our side. But obviously, each year we will probably, or maybe more often, we will have an assessment of what we are using. But right now, it's very small.
Thank you.
Hi. Thanks for the presentation again. So I have a question about job stats and the integration with the NVIDIA GPUs. I guess it's you use this NVIDIA Prometheus like plugin, and it's built on top on DCGM, I guess. And DCGM, it's hundreds of metrics that you can choose. So how difficult is to integrate new metrics? Because I'm not sure if you are collecting all the metrics or you choose which metrics you want to export, and how then it reflects to job stats. And maybe if you have other hardware like AMD, you want to use OmniStat, so how difficult would be?
So we've not curated a lot the metrics that we're collecting, right? So at the moment we're collecting everything, and we don't have a lot of GPU use cases at the moment. So we are not sure exactly what will be useful and what will not, right? Also, we don't want to spin up GPU instances just to test the monitoring. We can, obviously, and we've done it, but it's not something that we want to do constantly and see, okay, this metric is going to be useful, this metric is not going to be useful. It's not something we have explored a lot so far. And regarding other hardware, we haven't looked at it at all yet. When the time comes, we will look into it.
Maybe if I can add another question. So you use Grafana Cloud. And how do you deal with providing visibility to data to a set of users, so in a way that they can only see their own data and not, is it all this managed by the Grafana Cloud and like a role access space that you have on that? How does it work?
So for our setup, so the Grafana Cloud is only open for the admins, right? And we have a separate Grafana instance where we expose the metrics that we want to the users, right? So the users cannot log into Grafana and see all the logs of all the clusters, right? They only see the same metrics that Bettina presented earlier on the portal.
Thank you.
So what we did in terms of monitoring as well, it's integrating, let me move a little bit. So was integrating Grafana inside Open OnDemand, but using Keycloak as a bridge. So once you authenticate inside Open OnDemand, you're also authenticating inside Grafana, and then you can see the data that you want to expose in a template dashboard, so the users can see only their data. So that's a nice way to do that. So more questions?
Yes, we have a question from Slack. So give me just a second. No, it's not from Slack, it's from Zoom. So have you evaluated dynamic Slurm bursting to the cloud?
Yes. So one of the main problems with bursting, right, and we've looked at bursting to the cloud several times. One of the main problems with bursting to the cloud is what do you do with the data? Right? Your data is sitting on-prem. If you're working with imaging data, right, we're talking about terabytes and terabytes of data that you want to analyze. You burst to the cloud, okay, you get the instance in 15 minutes. But your data is going to take a couple of days to get to the instance. That's definitely not acceptable, right? So bursting to the cloud is convenient for some use cases. Some chemistry use cases, for instance, they have very small input data, right? They just need a molecule description, and then you can run for several days just on kilobyte input, right? But it does not fit all the use cases. We analyzed it. We deemed not worth the complexity of going through the bursting, and thought that providing isolated environments was a more flexible solution for us.
Thanks.
So I have another question. So for the job efficiency monitoring, so let's suppose that it's very unlikely this is happening, right? But imagine that you have a user that is underusing resources, like a lot. So you're going to see the report, you're going to see the data. What mechanisms, what actions are triggered after that? Do you need a human to review what this particular researcher is doing and then punish that person? Or are you automating a process to do something?
Well, you know me, right? And you know that I love efficiency. So if it were for me, I would kill these jobs immediately, right? No, what we have at the moment, this was implemented on-prem. We are not implementing this yet on the Juno environments, but on-premise, we have automated notifications to the users. Only once a day, right? They get an email with a summary of their jobs and the efficiency if it's under a threshold, right? If you're behaving properly, you don't get any email. Otherwise, you will get an email. And the cluster admins, after some time, if a user gets many emails or recurrent emails, they will contact the different support teams. So we are a support team for the pharma research organization. They will contact us and say, okay, work with this user because it's over-allocating resources or underutilizing them. So we try to take a proactive, reactive approach on this. So, but yeah, usually working with the users. We are not here to serve the technology, right? We're here to serve the scientists and our researchers. So as long as they can do their job and we don't have enough capacity for everyone, everybody's happy, right? When we start having capacity problems, then we work with the scientists to optimize their workloads.
So, and on Juno, what we can also do when we see this kind of pattern is also teach the user to use different kind of resources, because we have the ability to tune the queues to add different type of EC2 instances, because maybe at the beginning we got 2 big instances and we can shrink that down and give them access to smaller instances. So they will burn less resources by having a more tuned small instances, for example. And that's what we can do easily just by changing the Slurm configuration.
Good. So any other questions? Otherwise, please join a round of applause. Thank you so much.